Thank Professor Gillard for the kind introduction. Can you see my?
Yes, yes.
Okay, good, thank you.
That's fine.
The topic of my presentation is study of resonance issues between double-fed induction generator-based offshore wind farm and HVDC transmission. Here is the outline of the presentation. First, the motivation of the work, then a system description and modeling. Then it follows the impedance-based resonance model analysis, considering various wind farm operating conditions and the potential damping strategies. In the end, conclusion to this work. Over the last decade, many offshore wind farms have been developed and integrated into grid through HVDC connections. Here is a typical configuration for such application. The interactions among wind turbines, HVDC converter, and the passive grid components can introduce wide frequency range of resonances, which may amplify the harmonic distortions or endanger system stability. Their consequences might be the tripping of wind turbines, blocking of HVDC converter, or the damage of sensitive components. The objective of this study is to accurately characterize the resonances, evaluate their risks, and provide guidelines for the design of mitigation strategies. So here is the test grid, which is a 400 megawatt DFIG-based offshore wind farm with a 2-level VSA-based HVDC connection. The wind farm medium voltage collector systems are aggregated to two wind turbines from 80 wind turbines, and the wind farm is connected to the HVDC converter station through two short high voltage AC branches. The overall offshore grid can be considered isolated from the main onshore grid, provided that constant DC voltage is maintained for the HVDC connection. And for the resonance analysis, the transformers and cables are modeled using short circuit impedances and nominal pi sections. And for the HVDC converter, a decal frame single loop PI control is used to regulate the AC voltage. Its output sequence impedances can be simply formulated using the harmonic linearization analysis. For the double-fed induction generator-based wind turbine, phase locked loop is used to synchronize with the grid voltage. The whole dynamic of the system can be separated into 3 parts, namely the AC and DC side dynamics of the grid side converter, the AC and DC side dynamics of the rotor side converter and the induction machine, as well as the DC side dynamics. Jointly solving the dynamic equations can give the output impedance of the output admittance of the wind turbine. And furtherly, the admittance, decal frame admittance can be transformed to the sequence impedances using matrix manipulation and frequency shifting. Then the derived analytical models are validated through simulations. In this figure, the solid lines represent analytical models, and the asterisks and circles represent simulation results. Notice that the frequency couplings between the sequence impedances are neglected for simplifying analysis. Also, using these analytical it can be observed that these models match well. And the analytical models have the following drawback especially for high frequency dynamics. The pulse width modulation and the sampling process are simplified as a pure delay, using which the sidebound resonances of the switching frequency cannot be identified, as reported in some recent publications. As for the impedance characteristic of the HVDC converter, at low frequency area, the adopted two-level VSC is capacitive, while the MMC adopting same converter level control will be partly capacitive and partly inductive. For the frequencies above 100 or 200 Hz, the two-level VSC and the MMC will have nearly the same impedance responses. As for the aggregated modeling of the medium voltage collector systems, all the wind turbines can be considered in direct parallel connection due to the negligible series impedances of the collecting cables. Then they can be aggregated to a single wind turbine by scaling their parameters. And applying the equivalent power loss-based aggregation, as well as the accumulated capacitive effect of the cables, the whole MV collector system can be reduced to a single machine system. In the end, the aggregated model can reflect the change of the switching states of wind turbines and the cables in the detailed wind farm model. Then, according to the grid component connections of the test system, as shown in this diagram, the sequence subsystem nodal equations can be formulated. For the purpose of resonance identification, the derived nodal admittance matrix can be furtherly transformed to the model impedance matrix. This figure shows the frequency scanning to the model impedances. From the curve peaks of the magnitude plot, the resonance points can be identified, and from the phase plot, the stability of the resonances can be evaluated, namely a larger than 180-degree angle variation around the resonance frequencies usually indicates resonance instability. Then to find the resonance sources of the system, bus participation factors analysis can be conducted. The results to this case are presented in this table. As observed, for the resonance modes up to several hundred Hz, all the buses have more or less contributions to these resonances. While for the resonances above 1000 Hz, either the buses in the high voltage side or the buses in the medium voltage side are the resonance sources. This slide presents the impact of low rotor speed on resonances. Two practical conditions for the low rotor speed in offshore wind farm will be the low wind speed or the downward regulation of the wind turbine feed-in power. For the simulated wind turbine, it will maintain 1.2 pu nominal rotor speed when the when the active power is above 0.75 rated value. Once the wind power drops below this value, the rotor speed will be reduced following this equation. Then this figure shows the model impedances under different rotor speeds. As seen, when the rotor speed is reduced to 0.8 pu, resonance instability can be seen by the larger than 180-degree angle variation or the negative real part values. Then this resonance instability phenomenon is validated through simulation in MATLAB Simulink, as can be seen after varying the wind speed from 50 meters per second to 5 meters per second. The reduced output power of the wind turbine, as well as the reduced rotor speed, will finally lead to the diverging oscillation as the rotor speed approaches 0.8 pu. And the FFT analysis to the PCC voltage in this time window verifies the resonance frequency around 10 Hertz. This slide presents the impact of switching states of collector feeders on the risk of resonances. Practically, either individual wind turbines or the whole wind arrays can be disconnected from grid. For the case of disconnecting the collector feeder breakers, the model impedances under different scenarios are shown here. As can be seen for the frequencies above 200 Hertz, the variation of the grid topology in the wind farm can lead to enormous variation of the resonance frequencies. And for the critical one array stay connected in grid scenario, larger resonance peak is observed at around 350 Hertz. Then as for disconnecting individual wind turbines from grid, which can be realized by disconnecting the transformer breakers or the turbine branch breakers, these two cases are presented here separately. For different scenarios, for opening the transformer breaker cases, two resonance peaks can be observed at around 350 Hertz and 1450 Hertz, which tend to amplify the typical 7th harmonic and the HVDC converter switching frequency. For opening the turbine branch breakers, the variation of in-service wind turbines have mainly impact on this resonance modes. Then these two sharp resonance peaks are validated through simulations. As can be seen in this PCC voltage and current waveforms, after disconnecting 74 wind turbines from the grid by opening transformer breakers, large harmonic distortions are observed. The FFT analysis to this time window shows that the 7th and the 29th harmonic component violate the harmonic distortion limits as recommended by this IEEE standard. Then according to the above analysis, theoretically, the resonances can be shifted over wide frequency ranges. In the practical offshore wind farms, the more complex operating conditions and the grid topologies may increase the risks of the resonance issues. To enhance the power quality and stability of the system, wind turbines and HVDC converter can be configured to provide damping services. However, due to the
conclude in 1 minute, please.
Yeah, due to the restrictions of their switching frequencies, only the low and middle frequency resonances can be effectively damped. And two possible choices for damping the high frequency resonances can be installing active dampers with higher switching frequency. or passive dampers. The choice of the damping strategy may depend on the overall evaluation of the performance and the cost. So a brief conclusion to this work. Impedance-based resonance analysis was presented in this work. Subsynchronous resonance stability and harmonic distortion issues were demonstrated considering various operating conditions, and potential wide-band damping strategies are presented. In the future, design-oriented resonance analysis is still quite important considering the constantly evolving offshore grids, which can be featured with wind storage combined operation, multi-terminal HVDC grids interconnecting many offshore wind farms, or grid-supportive water controls. Thank you for your attention.
Thank you for your presentation. Very interesting. Other thing in your presentation. I don't see any question yet. So, I have a question about why are you studying the double feed injection generator for this kind of wind turbine, offshore wind farms? Right? Because you are speaking of 5 megawatts double feed induction generator, but well, for this power, most of the time it's a full converter. And have you done both studies, one on the DFIG, the other on the full converter, to see if there are some differences which comes from the technology?
Thank you for your question. I haven't conducted the study comparing the different by comparing the DFIG and the full converter wind turbines on the resonances of the offshore grids. Yeah, it's true. Currently, most of the offshore wind turbines are full converter based. However, in the German North Sea, there is a DFIG-based offshore wind farm with HVDC grid connection. So I think maybe in the further works, I can compare do some studies on this.
Okay, so I see that you have a question from Philippe Derouer. So can you answer to his question? Power level has an influence on the resonance around 10 Hz. Does the network topology change? If not, can you explain the link between power level and resonance?
I cannot see. Could you repeat the question? I cannot see the Q&A.
You can see that. So you show that the power level has an influence on the resonance around 10 Hz. In that example, does the network topology change? If not, can you explain the link between power level and resonance?
Sorry, I still cannot understand the questions well.
Okay, so
maybe I'll try to see the current question and answer. And
yes, you can answer after, because we have to.
by writing.
Yes. So thank you for your presentation.